Oh, the slam it on the desk method works.
So in today's video, this is my RC2014 that you've seen before. Currently only has inputs through a serial connector, and that's great and everything, but I've got this board now, which is a 2-player joystick port, and I figured I could build it and then we'll see what we can do with it, make it work. It comes with a couple of ICs that connect the data and the address to the joystick ports, which are old style 9-pin deconnectors, so I'll go and root out an ancient joystick. We'll have a look at how that functions too. And then it's got various other bits and pieces, so I'm just going to build it. Today's flux is this really awful lead-free, bought it from a cheap random shop. It's not very nice, it blobs up, it spits at me, and it just doesn't flow. It also gives off copious amounts of smoke. Not a fan. It's got flux in it that when you try and clean it off, it just turns sticky. As you can see, I've just bridged a connection. Yeah. Oh, the slam it on the desk method works. Cool. Okay, so I just learned if you smack it really hard, you can shoot the solder out the holes. I'm sure that's a proper technique there. Right. So now we have to attach this little 9-pin connector to here. And it goes in there like that, but I don't want to just attach it using solder because I'll end up probably ripping that straight off. So I need to put something through the little holes and then through here. So I think some component leads might work. It's long enough if I bend it into a U shape. That should work. Right, that's on quite well, but I've owned old computers like Atari STs where the joystick ports just pull off after a bit, so let's try and attach that even better. Give it some strain relief. So if I heat this pad up, fill that hole with solder, fill that hole with solder as well. Now we need to get some in there. Now, what you can't see is while I'm soldering, I've been spat at by pieces of flux out this solder. I'm not having a good time with it. That's on. Yeah, that's not going anywhere. Look at that, lovely. That's it built. However, the observant amongst you will notice that there's a connector missing, there's a chip missing, and there's a random chip in a breadboard. There's a reason for this. So this chip here is a 3 to 8 decoder, so you feed it 3 bits and it switches on one of the corresponding pins. So it's used for deciding which of these chips we're going to read from. This is the data bus, so these pins here are connected to these pins, which is the data. So that one is connected to that chip, which then goes to these pins down here. You can switch that chip on by sending a correct binary sequence of bits to this chip, which then enables this one. This chip here should be the same. However, I've been sent this, which is a 8-way D-type latch, or D-type flip-flop. This is used for output, this is used for input. So I've accidentally been sent a chip for using in an output board. This is an input board. If I put that chip in here, bad things will happen. It won't work. So I could either get another one of these chips and finish this board off, or we could do something much more interesting. I could try and make this chip work in here so that port 2 is an input. None of these pins really match up and the functionality isn't correct, but if I can match these pins to where they should go on here, I can then turn port 2 into an input, an output. And then I could connect something here, like LEDs or something, and then I could turn them on and off using code. And then this can be an input. So I think I'm going to try that. These are some random notes I've been taking. These are even more random notes. And then I have a handful of jumper wires. So the idea is that I can jumper the correct pin into the socket, wiring that up as an input instead. Because the address selection logic should be the same, because all it's doing is enabling whichever chip so that the data can be read or written to the bus. But first I think I need to check that the input here works, and then we'll move on to doing that later. This is getting quite full now, isn't it? Looks quite nice. You know, I can stick that in there, and then that's where the joystick goes. Right, look at this. This is the joystick we're going to use. It's a nice funky 90s colour. Being from the 90s, it features things such as a stick to hold on to that moves in 8 directions, 2 buttons, but actually they're 2 separate buttons connected together. So you've got 1 fire button, 8 ways of moving. Full of micro switches too, which is really nice. On the end of the other end of the cable, we've got this strange contraption. This is a 9-pin joystick connector of the what they call Atari standard. This is a weird Sinclair one that Sinclair used on 2 computers and then nobody used ever again. Weirdly, you could have a Spectrum with internal joystick ports that worked with this one, and then you could plug in an external joystick port which used this one. And if you plug that one into it, it could sometimes shut your computer out. So, very strange. If you had an Atari or an Amiga, you used that one, and probably wondered why that existed. Since this is nearly as old as me, I think I bought it when I was about 10. I've owned it for most computers I've had, or it's sat in a box. I'm going to open it and we'll see what's inside it, because it was designed for circuitry like this. It's not like an Xbox controller. It's got all sorts of electronics inside it and transmitters and circuitry to work out if you're pressing too many buttons at once. This is literally a bunch of micro switches. The exact same idea as the inside of an arcade machine. So if you look, the stick moves and it's just pressing each of these micro switches. And in fact the switch for the buttons is one that is connected together. So it's not even like there's 2 switches and I could hack it to make 2 buttons. This is literally a 1-button joystick. So I need to clean these because some of them don't quite work properly. Spent many hours playing games with this. That's probably bits of me just there, look at that. So, a bit of contact cleaner. Now this joystick's quite interesting. It features this turny thing that is now completely broken, and it adjusts the tension. So there's like little markers here, but the thing's up here, so let's see if I can fix that as well. You know, they used to hand assemble these joysticks in the factory. Don't imagine that was a fun job. There, that's even better. So you could have it on setting number 1, and the stick is nice and loose. Setting number 3, add a bit more force to it. There's a spring inside that you're tightening with this. That was this thing's unique selling point, along with its crazy colours. You'd buy it because of this thing. So you could have loose and floppy, or nice and hard. I'm not sure the fire button works anymore. Let's work out which is the fire button. So each hole connects to one of the different pins, and if I get my multimeter I can work out which one is which. So there's always a ground connection, which is pin 8, which is that one, and then I want to check the fire button works, which should be pin number 6, which is that end one there. So now I need 6 pairs of hands. So hold that there. What kind of rubbish reading is it doing now? Oh, let's try a different pin. Right, I've put the joystick together wrong. We're going to have to take it apart. That sounds more like it should do. Fun fact, they put suction cups on the bottom in the hope that you could suction it to your table and then not have to hold it in your hand. These suction cups never ever worked. They could have just replaced them with some sort of rubber feet. Because if you hadn't figured it out yet, this was not supposed to be a handheld device. You're supposed to have it like this and do that. Everybody though held it. Or if you're wrong-handed, that way. Right, they sound much better. So now this is the board we're plugging it into. and I've only wired up one port like I said before. Right, so it might be useful to go through how these joysticks get wired up and how I had to slightly modify the board so that the joystick I own matches the board. So this is known as the Atari standard. It's what Atari invented to begin with, and it follows this really simple pattern that the first 4 pins are the direction, up, down, left, right. There's then pin 6, which is the button, and pin 8, which is ground. So the way these joysticks work is voltage comes out of each pin from the computer. It's then grounded by pressing the button or moving the stick, and that goes into ground, and the computer can sense that. On the joystick board that I've got, it kind of works the opposite way around. So instead of voltage coming out the pins and going through down to ground, it goes the other way. So voltage goes into the joystick, you complete the circuit by pressing the button, which then sends the voltage down onto the data pins. Now, there's a slight wiring difference with this that it took me a while to figure out. According to the schematic for the board, pin 8 has voltage going into it, but on here, pin 8 is actually ground. Now that is okay, it just means it's like opposite logic, but really the actual physical board that I own, pin 7 is where the voltage goes in, and pin 8 is not connected to anything. And that's a bit of a problem, because on here, pin 7 is not connected to anything. There's no cable there. If you look on this connector, they've even like drilled out pins that have no connection. And one of them is pin 8, because pin 7 is the one it's supposed to be. So what I've had to do is bridge across them there, and then that makes it work. So yeah, this schematic is not quite the same as this board, but it's good enough, and I can figure it out from just tracing out the pins. So what we'll do now is plug this in, and have a look at some code. Here's the computer again. Here's the joystick board. We need to put this in this. I've got a multitude of sockets. I'm going to use a front one, just so I can easily see it. Where's that not going in? It's in. Right. And then I can connect the joystick like that. Attach the serial connection. Okay, so here we are. We're in the monitor again. Been here before. And I can show this works. If I get the joystick and I hold down a fire button, and then I type I1, it shows 10. And if I move it to the right and type I1, it shows 8. So if I do left and 1, or right and 1 even, it shows 18, because 10 add 8 is 18, funnily enough. That's how it works. But really, how's it work? Well, that's the interesting bit. So, here's how it works. We've got port 1, which is this one here. So when I press fire, we'll go for, I'm connecting 5 volts through pin 7 onto the fire pin, which is pin 9. So 5 volts is coming out this pin now, because it's gone through the joystick. It's going down here, through this, into ground, but then enough of the current goes through here into this octal bus transceiver chip, which is just a nice way of shielding all the data lines from all these nasty noisy switches, and people may be shorting things out by accident and plugging things in when the power's switched on. All kind of things you shouldn't be doing to a computer when it's switched on, but we do. So this just buffers the connection between the two. It doesn't actually do anything else. You just switch it on and it allows data to go between them. If you switch it off, it's like this chip is switched off. So that means we need to switch this chip on, otherwise the data will never come out onto the data line. So this comes down here onto the data bus. So if I want fire, it's going to put a 1 on pin 5, so that's 1, 2, 4, 8, which is 16, which then it shows it as 10, because the monitor shows things in hex. To turn this chip on, we need to make this chip switch on. This chip is the decoding logic. So it takes a binary number between 0 and 7 and then switches on the corresponding pin. So if you look, the chip enable is connected through to 5. So we need to make 5 on here. Well, that's 1, that's 2, and that's 4 in binary. So we need to ask it for 1, and then this one here, which is connected to the right pin. Now the right pin is always high unless you're writing, then it goes low. If I try and read from a port, this will go high, so we get 4, and then we have 1 here, which makes 5, because I'm asking it for port 1. It's really confusing. Okay, there's 16 address lines. That is the first address line, but we count from 0. But if you put a 1 on the address bus, that pin there goes high, which sends it into here, combined with that one, means we'll turn on that, which turns on that chip, which means that when you press the button, it connects 5 volts through the joystick to the pin, through here, onto the data bus. And then that will put that one on, which is 1, 2, 4, 8, 16 in decimal. We'll go on to here, and then 16 in decimal is 10 in hex, which is why on here, if I hold down the fire button and press I for input and port 1, I get 10, because that 1 is literally being sent up the address bus. So if I asked it for 2, there'd be 0 there, there'd be 1 here, combined with that, which would turn on the other port, which isn't connected. Now it's all great and all, being able to type in I1, whilst simultaneously pressing a button on the joystick and pressing enter and seeing a number, but I've got a slightly better program that I'm going to put on that will show each button as I move the joystick about. So let's get on with that bit. I've written some assembly code that will check each button and then print on the screen which button you've pressed, and we'll go into what this does in a minute. But first, here's how I get it onto the computer. Last time I was using the monitor, wasn't I? I was manually typing in code and getting in a mess with addresses and all that kind of carry on. What I have now found and sorted out is a much better system. So I can write my code like I should be able to on the machine like this, just using a text editor. I'm using Visual Studio Code because it works quite nicely. It works in Linux and Windows. And then what I've also got is a little build script that runs this assembler, and what that will produce is a Z80 output, but then I can't load that into the RC2014 because it has no file system. You can't click on file and open or anything like that. You still have to paste things in through the monitor. However, if you convert it into what's called an Intel hex format, which looks like this, it's just all the bytes from the file written out as ASCII characters with some extra data at the beginning to say where in memory it should go. If you copy that and then just paste it, it understands what this is. And now if I look at memory, so if you look here, I said it's starting at 8000 in memory, and here it is. Look, load DE with 8081, which is where start text must be. I do like in Linux that you can scroll a background window without losing focus on the foreground window. Which Windows did that? It's like focus follows mouse, but window raising is on click. So I've defined some text down here. There's a variable to store which button I've pressed, and then this code just works out which button is which and prints it on the screen. So if I run it, I'll get my joystick, press up. Now, I appear to have broken it, so this is a good chance to show you how I do this. So I'm going to reset that. Go on here, what's missing is the new lines and everything. So I guess I've not compiled this because they're correct. So all I do is I hop in here. I've written a little script which doesn't do much. There you go, it just runs a couple of programs with various switches so that I don't have to keep typing it in. So I do that, it's compiled it. I've then got the hex file which is here. Copy it, go into there, paste it. There we go. So I've got fire button, up, down, left, right, up right, up left, down right, fire and right and down, up and left and fire. If I could press up and down at the same time, that would work. There's no form of debouncing or single shot, so it prints it as many times as it's capable of doing on the screen at once. But there we go, this is a much easier way of coding. Definitely using this more. It's a much easier way of uploading it. And it's just as quick. I can very quickly figure out what I'm doing, which is the whole point of this, understanding everything that's going on. So what I've managed to achieve is getting a joystick, working with the machine, and being able to write more efficient assembly and see what it does. So the next thing I want to try is to turn this port here into an output. And in theory, I should be able to do that by using that chip that I was mistakenly sent. But then I have to rewire this socket. So I might prototype it on a breadboard first and see if I can get it working. But now I've been through making this work, I understand more about how all this is going on. So adding this shouldn't be too difficult. So we'll see. But that's it for now. If you want to know more about this thing, you can either search for their website, or if you look on some of the other videos that I've done, you'll be able to see what else I've been trying out with this. I built all this from components, and one day I want to make a board of my own that goes in here that possibly allows some sort of screen to attach to it. Maybe not this one, but it'd be nice if it had a screen. So there you go. Thanks for watching, and I'll see you again. And next door's dog is having a bark.